To study more precisely the phenomena at work in RNN, we are first going to focus on how to compute the gradient in such networks. We will then see penalization and weight initialization methods and explain two variations around RNN, GRU and LSTM units. So first, how to compute the gradient in RNN. A classical RNN architecture is displayed here. The loss is represented here in red as the average of the loss obtained at each time. Now consider the loss L4, which appears at the top right of the picture, and try to compute its gradient with respect to the weights of the network. Now, can you compute the gradient of the partial loss L4 with respect to the weight matrix WHH only? You can take some time to think about it. Don't hesitate to pause the video. The backpropagation equation used to compute the gradient is given here. To obtain this equation, note that the matrix WHH appears in many different places in the network. More precisely, it appears each time you have an arrow from a hidden state to the next hidden state. You can then apply the chain rule to derive this expression. Indeed, following the arrows that go to L4, we obtain that the derivative on the left is equal to the derivative of Lt with respect to y hat t times the derivative of y hat t with respect to WHH. Since WHH appears both directly in the expression of H4 and in the expression of H3, you can apply the chain rule. Similarly, WHH appears both directly in the expression of H3 and in the expression of H2. Applying the chain rule recursively through the hidden states of the network gives the backpropagation equation. The backpropagation equation is displayed here. Note that we have a sum over k ranging from 1 to t, which corresponds to the different times, steps, hidden states in the network. This formula is quite generic since it does not depend explicitly on the expression of hm. If we recall that hm is given by an hyperbolic tangent applied to a linear combination, the partial derivative of hm with respect to hm-1 is given by the second formula. Note that here we compute the partial derivative of a vector with respect to each component of another vector and store this result in a matrix. We have also omitted the bias terms for simplicity. This formula is going to help us to understand a major problem of RNN. Can you detect this problem? You can take some time and pause the video. Remember that for RNN, the problem of vanishing or exploding gradient phenomenon may arise. This phenomenon corresponds to the fact that the components of the gradient in the first layer of the network are, by construction, either very large or very small. Here we are going to see a problem in RNN which is related but different from the vanishing, exploding gradient problem in RNN. In RNN, we use the hyperbolic tangent whose derivative is smaller than 1. Thus, as for RNN, backpropagating the gradient through many hyperbolic tangent functions automatically decreases the gradient. More precisely, if we assume that the largest eigenvalue of the weight matrix WHH is bounded above by a constant, we obtain that the norm of the gradient of Hm with respect to Hm-1 is smaller than eta. In turn, the product of the norm of the gradients is smaller than eta power t minus k. You see that when t minus k is large, that is when k is small, this term is close to 0. It means that this term, which appears in the backpropagation equation, is really small for small values of k. Small values of k correspond to the first hidden states in the network. Consequently, when these gradients are small, the network forgets that the weight matrix WHH appears in the first hidden layers. It forgets about the long-term dependencies between the prediction and the first hidden state. This can make the training of the network difficult. The weight matrix is likely to change based on the last prediction y hat 4, but the network will forget that changing the weights will also change the first prediction of the sequence. It can thus lead to some instability in the network training. Concretely, it can be difficult to translate a sentence. You may need the first words of the sentence to translate the end of the sentence, but due to the previous phenomenon, the network cannot use the information of the first word in the sentence to predict the end. Note that this phenomenon is different from the vanishing gradient phenomenon, since here, no components of the gradient is going to 0, which was the case for some components in RNN. Instead, for each component, the long-term dependencies disappear. Therefore, we will talk about the lack of memory of RNN instead of the vanishing gradient phenomenon, even